Ma chambre a la forme d'une cage. Le soleil passe son bras par la fenêtre. Les chasseurs à ma porte comme les petits soldats qui veulent me prendre.
This is Steve Saltwick. Welcome back to Your Brain, a Personal Tour. Today is Seminar 3, The Structure of Memory. Now, memory is a slippery term. Some people use it one way, some people use it a different way. For today, we'll use a definition of memory, that memory is the storage and retrieval of knowledge about the world that changes our behavior. And we'll look at memory in three different aspects. First, what are the critical parts of the brain that stores memory? Second, do memories move around in the brain? Someplace in one part of the brain early on your experience with the world, someplace in a different part of the brain. We'll take a look in this seminar. And lastly, third, can we manipulate memory to relieve human suffering? And we'll see that recent research points to very promising avenues of research to relieve significant human suffering. The subtitle talks about Marcel Proust, who was a French literature writer who wrote about detailed, dense memories, much like videotapes of an experience. Are memories like that? Or are they like totem poles? Now, totem poles were carved by Pacific Northwest Indians, and they dealt with the essence of the story. They had to be reinterpreted by a knowledgeable person. And our memories like that, we'll see that there's a combination of memories. So sometimes they're a little bit like Marcel Proust, sometimes they're a little bit like totem poles, and today we'll describe how they start one way and finish up in another. Welcome to the seminar. I hope you enjoy it. Memories can be verbal or nonverbal. In a verbal memory, one way to experience it is like a Proust story. This is a rich and detailed recollection of an event, perhaps long past. Proust wrote a story about a famous Madeleine that he enjoyed on a cold winter's day with a warm cup of tea. It called forth almost reflexively a rich and detailed set of memories about times long past. Pacific Northwest Indians tell a story related to totem poles. Totem poles reflect the gist of a story. To give you a good example from a Western culture, the totem pole for Goldilocks and the Three Bears would be a bear, a bowl, and a bed. A knowledgeable storyteller would recreate the story from this mnemonic device of a totem pole. Note that means two different storytellers might tell two different versions of the story, or the same storyteller telling the story at one time compared to telling a story at another time might also get slightly different stories based upon the reading of the essence from the totem pole. But there's a third kind of memory, and this memory is not verbal at all. It is a change in structure that encodes our interaction with the world, and then behavior is different because of that. Look at this field. Water in this field has previously interacted and resulted in a gully. Future applications of water in this field will behave very differently because of this gully compared to when the gully wasn't there. So this is a memory too. It is a memory not involving words, but of a change in structure of the environment. I want to begin our discussion of memory with a personal encounter of my own. This is me about to undergo my second hip operation on the 16th of June, 2014. I'm accompanied by the brilliant surgeon, Dr. Shelby Carter. I'd had my first hip operation in March of 2014, and it was extremely helpful. I just couldn't wait to have my second hip operation to fully enjoy the benefits of having new hips in an old body. But this picture almost didn't happen because a few days earlier, on June 10th, 2014, I had the following conversation with my wife, Becky. I was sitting at the breakfast table drinking coffee when Becky entered our kitchen returning from work. She said, "Why aren't you at the doctor's office?" I said, "What doctor's office?" Becky said, "To prepare for surgery." I said, "What surgery?" Becky said, now getting a little concerned, "For your other hip. Time to do the right hip." I said, "I've never had hip surgery." Becky, now getting very concerned, goes, "Yes, you did, in March of 2014. I was very frustrated now, and I said, "No, I didn't. If I did, I would have a scar." And then I proceeded to show her how I had no scar. At which point I said, "Oh no, I have a scar." And then finally, much to her credit, my lovely wife Becky goes, "Let's take a little car ride." She didn't tell me we were going to the emergency room, but that's where we went. As we drove to the emergency room, it became clear that there were some things that were not quite working with my memory. For example, I did not remember going to India in January of 2014, approximately 6 months before we were driving to the emergency room. However, I did remember Becky and the dogs. I could remember the layout of my home. I knew where to go find my shoes. I remembered how to put my seatbelt on. So I remembered the habits that one normally had. I could ask reasonable questions. So, for example, I asked, if I had hip surgery, then I would have a scar. So I could do deductive reasoning. But I had a big problem. And that problem is illustrated in the following dialogue that we had as we drove along. Becky would ask, "How are you doing?" I would say, "I had hip surgery." "Yep, 3 months ago." "Where are we going?" I had hip surgery." "Yes, look at your scar." "Really? Are you sure?" I had hip surgery." "Yes, you had hip surgery." "Where are we going again?" This example of conversation shows that I was clanging. I could not incorporate the context of what was happening right now into my memory. I could focus on it for a little while, but then distracted or looking at something else, whatever, I would return to the fact that I just could not represent I had had hip surgery. And this leads us to look in some specific places for where my problem lay. Now, after a 24-hour battery of tests against my body, my brain, my heart, my blood flow, etc., in the emergency room it was determined that I probably had an interruption of blood flow to the brain via the internal jugular vein, which caused an old friend of ours, my hippocampus, to reset. In essence, the interruption of blood flow caused my hippocampus to reboot. It restarted. And as a function of that restarting, that's why I had the memory episode that I did. And we'll use that to set our framework now of where are memories, how do they come about, etc. Because I assure you, when your hippocampus has a hiccup, there's definitely an impact on memories. Now, if you talk about memory, there's a specific animal that often springs to mind: the elephant. Legendary for their memory, it does turn out that elephants have a hippocampus 40% bigger than a human hippocampus, prorated for body weight. It also turns out that elephants have one of the most complex societies on the planet. They comfort others, perform death rituals, and honor their elders in a matrilineal group of 4 to 5 females. The association of the hippocampus with a complex society is the first hint we have that there might be something more to the hippocampus than we first studied, and that's important. But there's also another good reason to be aware of the elephant and the hippocampus. And that is because the elephant is only distantly related to humans. Our family tree diverged about 60 million years ago. Elephants are most closely related to manatees. So if elephants and manatees have a hippocampus, then the hippocampus is a fundamental building block of memory for virtually all mammals. We can learn a lot from studying how the hippocampus works in such widely diverse species if we can keep them around. And how for keeping them around is one fortuitous outcome of research on elephants. Nowadays, poaching is not the most pressing danger for elephants. Competition for forage with native farmers is the new challenge, who often kill trespassers on their fields. I'm thrilled to note that as a result of some practical scientific research, it has been shown that elephants are truly scared of only two things: humans and bees. The bees can sting the end of the trunk or around the eye, and that makes even a bull elephant cower. As a result of this research, enterprising farmers are now constructing low-cost bee fences. The hives are hung between poles, with two outstanding results. Everyone can afford to protect their field without killing elephants, and the collected honey can be used for food and/or a cash crop at the market. If that's not a win-win, I don't know what is. In our last seminar, we looked at the hippocampus and found that there were unique neurons within the hippocampus called place cells. Those cells fired when the rat or the animal was in a particular part of space. Well, as it turns out, the hippocampus is much more than place cells, and we'll look at that in this section of the seminar. To make a long story short, the hippocampus is essential for what is called episodic memory. A good example of episodic memory are, can you remember where you were and what you were doing at the time of 9/11? Can you remember where you were and who you were with and what you were saying when you learned of the assassination of John F. Kennedy? Or when Neil Armstrong stepped upon the moon and remarked his most famous phrase? These are autobiographical memories, almost like a Proust story. They are rich, they are detailed, we remember them vividly. And as it turns out, the hippocampus is essential for this kind of memory. I want to refresh your memory about place cells and how they relate to a rat thinking about a path. When a rat runs in a maze in real time, he goes through a series of spatial locations. Take a look at the maze on the right here. He would go through some locations that are coded in his hippocampus by different cells. There's a place cell for the purple zone, a place cell for the yellow zone, a place cell for the red zone, and the zones in between. And as the rat runs through that in real time, as he's running, these place cells fire. But there's another time that place cells fire, and these are as a part of something called a sharp wave ripple. Now, a sharp wave ripple is a very quick burst of place cells. They're about 1/10 of a second long, and these place cells fire in sequence. So in essence, when a sharp wave ripple occurs, the rat is thinking about a path. He's not moving in that path. This happens much too quickly. The rat is thinking about going on a path that can be described by the sequence of place cells as they fire. So you'll see on the bottom a sequence of place cells that are color-coded, if you will, within the sharp wave ripple, and that decodes to a trajectory that the rat is thinking about in a maze. As it turns out, that's not the only way that place cells fire in a sharp wave ripple. To give you an example, let's take a rat that's been trained to go through a maze to obtain a food reward. If we were to look at the way place cells fire in sharp wave ripples when the rat begins the run in this maze, we would see that the firing of place cells anticipate the path the rat is about to go on. So they fire in a forward manner. They describe an anticipated or future path of this rat through that maze. But once the rat gets to the food and starts to consume it, we see something very different, and that's shown on the right-hand part of this slide. The place cells fire in the reverse order. It's as if the rat is thinking, how did I get here? That's probably a good thing to remember. And also, recall that the reward system is now going to be active when the rat is consuming this reward. So at the time the reward system is active, place cells firing reverse order in these sharp wave ripples are basically laying down a path to this food that will be strengthened by the reward system. This is what underpins instrumental learning. And it's a very, very important discovery in terms of how place cells within sharp wave ripples show what is about to happen in terms of behavior of an animal, and also help explain how does an animal learn when they finally discover reward in some kind of maze or situation. As it turns out, place cells also measure time. And the way we show this is that we train a rat to run on a treadmill for varying lengths of time. And then if we look in the hippocampus, we will find cells that measure time much as if place cells measure the rats traveling in space. To give you a good example, look in the A section of the white part of this diagram. Here we see 4 hippocampal cells, A, B, C, and D, that measure the time intervals or portions of the time interval as a rat runs on a treadmill. Cell A marks the beginning of this time interval and cell D marks the end. And then B and C measure points of time within that. 3 different trials are shown here, so this is 3 separate episodes on the treadmill. Now, when you attempt to measure time with a rat running on the treadmill, you must be careful that you are not measuring the level of effort, how many footsteps or paw steps the rat has done on this treadmill. You've got to run controls that show, yes, indeed, these cells are measuring purely the aspect of time. And I assure you that these experiments run controls to rule out level of physical effort and other assorted variables. This is purely the measurement of time. Hippocampal place cells can also reflect learning, and we can show that with the following experiment. Let's suppose we take a rat and we find a place cell for position 1 in his cage. Position 1 in this instance is going to be where the red dot is, the lower left-hand part of the cage. There's another position at the top of the cage that we're going to call position 2, and we're going to train this rat that one of 2 flower pots can be in those positions. One flower pot, we'll call X, has a distinctive odor and it's always associated with food. So the rat can dig in the sand of this flower pot and always find a food reward. A different flower pot, we'll call Y, is never associated with food, and so we'll denote the absence of food here with a minus sign and the presence of food with a positive sign. X and Y are changed randomly between position 1 and position 2. Then after the rat has learned this task, we probe post-training for the response in position 1. Remember, position 1 is at where the red dot is, and we're recording from a place cell that is preferential for position 1. When X is in position 1, we find a very strong response from the place cell as shown below. That is very rapid firing and represents a strong indication for this place cell when a food reward is present in position 1. But what if Y? What if the food or flower pot never associated with food is present in position 1? Well, this is a place cell and it does fire, but it fires at a much reduced rate. So yes, indeed, this is a place cell, but the important thing we learn from this experiment is that the place cell does not just encode place, it also reflects the learning about that place, and that is essential for understanding what place cells really are. The other aspect of place cell behavior I want to talk about is how that they are exquisitely sensitive to small changes in the environment. Let's take a look at that in an experiment. In this experiment, we have the rat in a circular enclosure. We have electrodes in his hippocampus. We can monitor the firing of those neurons with a computer. And also attached to the computer, we have a TV camera suspended above this enclosure so we can track the physical location of the rat in space. Then, as a given place cell fires, we can map its place field with a color-coded diagram as shown on the right. Yellow here basically means no firing, and then in increasing density of color, red means firing a little bit, blue a little bit more, purple maximum rate of firing. We can map the place field of a given hippocampal neuron. But what we're going to do is something we haven't done before. We're now going to vary the environment with a very small change to, my eye and hopefully your eye. We're going to put a cue card along the wall, just one cue card along the wall in that relative size, and that cue card can either be black or it can be white. And we'll study and evaluate whether the presence of that card affects place cell behavior. And to make a long story short, it does, and it does dramatically. Shown on the right of this slide are several place cells and their behavior when either a white card is in the environment or a black card is in the environment. One particular place cell is shown in row A. This shows behavior of that cell and shows how different behavior of that cell is when white versus black is in the enclosure. When the white cue card is in the enclosure, it has two separate place fields along the edge of the enclosure, kind of south, east, and southwest in that environment. And when the black cue card is in there, it's a northwest kind of place. Now, this is not some kind of strange cell. There are three other cells in the hippocampus of that rat, shown in area B of this slide, that shows, again, dramatic changes in the place field of a single neuron in the hippocampus of that rat, which vary greatly depending upon whether the white cue card is there or the black cue card is there. What this means is that with very small changes in the environment, the expression of these place cells can change dramatically. So this allows the brain of this rat to distinguish these environments with really a very different constellation of space within the animal's brain. This allows the animal to distinguish the environment, one with a white card versus one with a black card, and that is essential to the formation of memory. So hippocampal place cells certainly represent a lot more than place. I assert that what they really do is build a context. Now, what do I mean by context? Well, let's take a familiar example. In an office, your office, there are many different kinds of elements, and those are shown on the left-hand part of this slide. There's chairs, there's a desk, there's a filing cabinet, there's a clock, there might be papers. All of those are individual, perceivable objects that are found in many different kinds of experiences. But an office context is an integrated whole of them in a particular place and at a particular time. So your office is a particular desk with a particular filing cabinet, a particular chair, a particular clock, particular papers, all integrated into a perceptual whole. That is what I mean by a context. And what is unique about this context, it has all the details of a Proust story. It's rich. You can imagine yourself within that context. And as it turns out, that is the essential function of the hippocampus. It encodes for space. It encodes for time. It is sensitive to small changes in that environment, learned associations within that environment, and all of that knowledge about the world, which can be used to affect behavior, which is our definition of memory, is held and processed by the hippocampus. Now, an interesting aspect of context cells is that they are active not just in the experience of that context, but in the recollection of that context. And we can see that in the following experiment. Here we have a human subject on an operating table, and we're going to record from single hippocampal neurons while he watches short video episodes. The title of the episode is shown on the slide. He's watching this on a set of eyeglasses, and we can see this particular hippocampal cell is really excited about Tom Cruise in the famous scene of him jumping off a couch on the Oprah Winfrey Show. This cell is not active to many other kinds of visual input, but really specifically about Tom Cruise on Oprah Winfrey. We'll now take off the goggles and just ask the patient to freely associate, think about what he saw, and tell us. So now he is thinking or recollecting about memories. We'll show his responses in text above. We've masked his voice for privacy. You probably can guess what's coming, so let's wait for it. So there you have it. A context cell that was active during the experience is absolutely active during the recollection. Once context cells are built in your hippocampus, they can be associated with other experiences. So the office context, if you have an aversive experience in that office, let's say a confrontation with an office worker or you're laid off or something like that, then that office context, much as we saw in associative decisions, can be associated with that averse experience. It's Pavlovian or associative conditioning. And one interesting thing about context cells is that their response can be evoked by just parts of that context. This is called pattern completion. So that when you remember or experience a portion of that office, then all the other memories associated with that can be called to the fore. So the presence of the office, that particular arrangement, can bring forth an aversive emotional response, not with the person present, but because the context is being completed by a subset of that pattern. So let's hear from Homer on what he thinks this section of the seminar really represents in terms of essence. And the first thing Homer would say is, Wow, place cells are really context cells. And not only for the perception of context, for the memory of context. The same cell that perceives a context is the one that's associated with the memory of that context. And that memory, from those little dudes of the context cells are the Proust of the brain. The memories are rich and detailed, whoever Proust was. So let's go back and think about what was happening in my hippocampus on June of 2014 when I had my transient global amnesia. One significant fact was that I couldn't incorporate things that were happening to me into the context of the current time. I had no recollection of hip surgery, and even though I was told that I had hip surgery, even though I saw my scar, I could not incorporate that into the context of what was happening now. I also couldn't remember the fact that I had been to India with Becky 6 months prior. However, I did remember Becky, I did remember our dogs, I did remember the layout of our house, so clearly I had some memories and I didn't have access to others, nor could I store the current context into my memory. So I still had some memories. The question was, where were they? And the answer to that means we have to look at dreaming and sleep. In The Tempest, Shakespeare says, "We are such stuff as dreams are made on, and our little life is rounded with a sleep." Shakespeare got it right. The creation of memories depends upon sleep. Life would be impossible without sleep. So your brain needs sleep, and we'll talk about that in this section. Dreaming is an activity of your brain during sleep. It's not essential. Certain antipsychotic drugs eliminate dreaming, and people still live healthy lives. But dreaming is something that has fascinated man for as long as history has existed, and we need to talk about that first. When we look at sleep, we'll see that it's divided into two main categories, as shown on this diagram on the left. There's something called non-rapid eye movement sleep, or NREM, and something called rapid eye movement sleep, or REM. We'll see the various stages and how sensation and perception varies across these modes of sleep in this diagram. Now, most people think that dreaming only occurs during REM sleep. And until quite recently, that was the output of research literature. But it turns out, as so often with research, the result you get depends on the question you ask. And if you ask the following kind of question as people go into non-REM sleep, the first stage of that, and we'll talk a little bit more about stages later, and rather than ask, "Are you dreaming?" if you ask, "Anything going through your mind?" you will get a dream report 80 to 90% of the time. Likewise, if you wake people up in a stage of deep sleep, there is something called sleep inertia, and it has a major effect on dream reports. People awaking from this stage of sleep need time to reorient, basically get back up to speed into what is happening in the now, and dream reports are very unlikely at this point in time. But if you sum over all the stages of non-REM sleep, overall dreaming is reported when you ask the right question between 25 and 75% of the time. So, clearly, we dream in all stages of sleep. If you also look at when do humans engage in rapid eye movement sleep, it turns out the vast majority of rapid eye movement sleep occurs in the womb. A baby before birth will spend up to 24 hours a day in rapid eye movement sleep. Then that sleep percentage declines over time, becoming almost vestigial once we reach adulthood. A fascinating theory is that REM sleep basically is movements being generated by a pattern generator in the brain that causes limbs to move, the baby's limbs to move in the womb. That then feeds back via somatosensory input back into the brain, and it helps various parts of the brain wire together. This pattern generator doesn't go away as we age, so there's still bits of our sleep where this pattern generator is generating movements that may cause our body to move. It may be shut down, but this is what causes active lucid dreaming in the latter parts of our sleep. Now, when it comes to dreams, there is a part of your brain that is intimately associated with that. We'll talk about this part of your brain in far more detail in Seminar 5. It is called the temporoparietal junction. It is marked on the diagram on the left here. And there's two significant facts we need to talk about right now. The first is this part of your brain develops after you're born. It typically reaches full development around 5 years of age, and it turns out the development of this brain area parallels the report of dreaming in children. Young children don't tend to dream. They tend to develop that capability over time, and that time frame matches the development of the temporoparietal junction. In adults, some antipsychotic drugs basically shut this area down. And when this area shuts down, patients report the global cessation of dreaming. So this is not dreaming during rapid eye movement, not dreaming during non-rapid eye movement. So there's something about this part of your brain that seems to be associated with dreaming. And in fact, it's associated with something far bigger than that, something that is unique to humans. But we have to talk about that in Seminar 5. Today, we're talking about memory. Now, one thing that sleep has unambiguously been related to is the reduction of synapses between brain cells. Recall from our previous lecture, a synapse is where two brain cells communicate. It's highlighted on the left in the red circle. This is something from the C here, where a sensory neuron was communicating to a motor neuron across a small gap. That gap is called a synapse, and this is essential to learning. Now, from studying a wide variety of animals, something as diverse as fruit flies, which are shown on the top, and mice, which are shown on the bottom, both are standard research areas to study synaptic density. And so you'll see an actual micrographic photograph of a synapse in the lower part of the middle of this slide. That's from a mouse, and that's what an actual synapse looks, where two nerve cells come together. Recall that we said the brain is encased in skull. The skull is of fixed size. So as you build synapses, you are increasing pressure in your brain. Something has got to give. Your skull is not going to get bigger. So the number of synapses, in essence, have to come down. There is a grand total that is kind of the maximum that your brain can have. So one thing that we have found through experimentation is that sleep reduces the net number of synapses in your brain. It, in essence, relieves the pressure of the daily learning that has just occurred. Now, that is an interesting fact, but there's even more interesting facts that can be discovered about the structure of memory and synapses in your brain. And we'll look at that next. The first fact we want to note is that these sharp wave ripples, these are these thoughts of a rat running down a path in space, are repeated in a certain phase of sleep called slow wave sleep. Let's look at that in more detail. On the left-hand bottom of this slide, we show a familiar diagram that represents what a sharp wave ripple is. It's a sequential firing of place cells in a very short period of time, and it can be decoded as a trajectory in space. The one on the lower left shows a rat running down a maze, turning right, and then turning right again and going up. That's encoded in this sharp wave ripple. It turns out sharp wave ripples occur during certain phases of sleep, and that's shown on the right-hand part of this slide. Sleep is divided into several stages, but for our discussion right now, we really only need to be concerned with two major divisions. The type of sleep that occurs in the first half of a nightly rest period is called slow wave sleep, and it's identified with certain kinds of relatively slow wave activity in rats, in humans, in virtually all mammals. In the second phase of sleep, electrical signals from the brain are quite different. This is called rapid eye movement, or REM sleep, and that's shown on the right-hand part of this diagram. Focus on slow wave sleep. This is where sharp wave ripples occur. We can see that in the rat EEG, and that's shown in the lower left. We can also see that in human brainwave recordings, or EEG. They're not called sharp wave ripples with humans, they're called spindles, but it's the same thing. So we see this representation of a thought being repeated in a certain phase of sleep, slow wave sleep. If those are related to the formation of memories, we should be able to manipulate them. And as it turns out, we can. To show this manipulation, let's set up the experiment first. We're going to take a rat, and we're going to put an electrode in the rat's hippocampus, and we're going to record place cell activity and sharp wave ripples. Our goal is going to be to create a memory, because if we can create a memory, then we can show how this is all related to the same process. So back to our rat. We're going to record from the hippocampus. We're going to also put an electrode into the reward system. Remember, we dealt with the reward system in Seminar 2. By stimulating the reward system, we can behave as if we have fed the animal some food or given him some kind of positive reinforcer. So we have two electrodes in the rat. One to monitor what is going on in a hippocampus, and the second to activate the reward system when we want to. And since we have a computer in control of all of this, we can pick out precisely certain patterns of activity in the hippocampus, and when those patterns occur, we can stimulate the reward system of the animal. Now, what are we going to do? Well, the first thing is we're going to take the rat, before we train them or do anything, and place them into a circular enclosure and let him wander around and explore the environment. That's shown on the bottom of the slide in section 4 of the white area. While that rat is exploring, we find a place cell. In this instance, the place cell is shown by a heat map of activity. So in the area that is red, that is where the place cell is most active. It turns out it's associated with the rat being in the bottom or the southern portion of that circular enclosure. Now that's while the rat is awake, and that's while he's moving around. We're now going to let the rat go to sleep, and we're going to monitor his hippocampus, and when that place cell fires, we're going to then stimulate his reward system. This is all done by computer. The rat is not moving around. It's as if he's dreaming about moving around. And whenever he dreams that he is in that location of this enclosure, we're going to stimulate the reward system. Then after the rat wakes up, we're going to take him and put him back into the environment he was in the day before. And lo and behold, the rat makes a beeline for that area of the maze associated with the place cell that we stimulated in his sleep. This is amazing. We have created a memory with the rat never experiencing food in that place, never experiencing the reinforcer. We've done this all electronically by monitoring the place cell of the hippocampus and then stimulating whenever that place cell fired during the sleep of the rat. So if we can create memories out of the blue by pairing sharp wave ripples in the hippocampus with reward system behavior, can we do the opposite? Can we disrupt learning and memory by disrupting sharp wave ripples? And it turns out we can. Let's take a look at a particular experiment. The experimental apparatus is shown on the left-hand side. There's an 8-arm maze. The rat's always put in the middle of that maze, and 3 out of the 8 arms are baited with food. Those are shown by the small red dots at the end of 3 arms out of the 8. Each day, we're going to give the rat 3 training sessions. So he's placed in the center. He gets to explore the maze. The object is to find the 3 places of food in those arms. He gets 3 trials. There's a 3-minute rest in between each one. And then at the end of 3 trials, there's a 1-hour sleep rest period. And during that sleep rest period, we're going to do one of 2 things. On rats that have been implanted into their, with electrodes into their hippocampus, we're going to monitor for sharp wave ripples, and whenever we see them, we're going to disrupt them. That's the test group. So we'll monitor for sharp wave ripples. When we see them, we zap the hippocampus, and we disrupt that pattern. In the control group, we're going to watch for sharp wave ripples, and then disconnected with that sharp wave ripple, we're going to stimulate the hippocampus. So both the test and the control group get the same amount of stimulation in the hippocampus. One, the test group has it so that it disrupts sharp wave ripples. The control group has it such that it does not disrupt sharp wave ripples. We have a third group that doesn't get implanted at all to make sure there's nothing about the procedure that might be doing anything funny in the results. And that's the experiment. We train these rats day by day by day with this kind of training paradigm. The results are shown on the right. We see that our control animals learn this task to a very high level of performance, greater than 90% over the course of 15 days. So by merely stimulating the hippocampus, disconnected from sharp wave ripples, has no real effect. It's as if the rats haven't been implanted at all. However, look at the test group. They're shown in red. The test group has a severe impairment on this task. By disrupting sharp wave ripples in the hippocampus, we are disrupting learning, we are disrupting memory. So we can manipulate memory, we can actually create them, and we can actually disrupt them by manipulating sharp wave ripples in the hippocampus of a rat. We can also show how memories can be improved during sleep with the help of the hippocampus. The experimental paradigm is in the top part of this figure. We're going to take human subjects and we're going to train them in a card task where when a particular odor is experienced, the subject has to pick 2 out of a selection of cards. So when odor number 1 is presented, then the subject has to pick 2 out of those cards in front of him. When odor number 2 is presented, he has to pick a different set of cards, etc. The reason we're choosing odor is that we want to manipulate the brain during sleep. Many of the sensory inputs to the brain are shut down during sleep, but odor is not. The olfactory system has a direct input to the hippocampus, and we can use that to our advantage in this experiment. As the subject sleeps during the course of a night, we monitor his brain waves, and when the subject enters slow wave sleep, and that's shown with the shaded part of the diagram above, we're going to represent one of the odors. In this instance, the scent of roses. Isn't that nice? In the middle of your sleep, you're going to get the scent of roses, and that's associated with 2 of these particular cards that'll be presented on the computer the next day. After a refreshing night of sleep with all this scent of roses, but notice we're only doing it during slow wave sleep, the subject is tested again. And now we'll find out, was there a difference by presenting that odor during sleep? The results of the experiment are shown in the middle of this diagram. If we look at subject performance where the odor was presented during slow wave sleep, we get a significant difference. The subjects that have experienced that odor performed much better. Presenting that odor during other parts of sleep, rapid eye movement sleep, as shown in the middle, or during waking, had no significant effect. And since we were monitoring the brain waves of the subject, we could find out what was the part of the brain that was most active when this odor was being presented during sleep, and that was the hippocampus. That's shown as this bright yellow spot in an image of the brain shown on the very bottom. So it's true for rats, it's true for human beings. The hippocampus in sleep is extremely important in the formation of memories. We're now ready to explore how memories move around and are changed in our brain as a function of sleep. And the bottom line here is that sleep produces totem poles. Remember, totem poles are the essence of the story. They're the distilled elements separate from all this autobiographical Proustian memory. We'll see now in this next session how sleep produces memories like this and where those memories move outside of the hippocampus. A good experimental program to use here is called the social transmission of food preference. That's a mouthful, but it makes a lot of sense if you think about it from a rat's perspective. In this kind of experiment, we take two rats. One's called an observer, one's called a demonstrator. We make sure they trust one another, if you will, by having them eat together some well-known food, like rat chow. After that, the rats are separated. So the observer goes away, housed in a completely different room, and the demonstrator is given some unique food. Turns out rats love cinnamon on their rat chow, and that's what we're going to feed the demonstrator rat. After this demonstrator has eaten, we bring the observer rat back together, and they socially interact. When rats do that, they smell each other's breath. After that, if we take the observer rat, this is the rat that's come back into the environment, and we present him two foods, neither of which he has eaten before. There's the cinnamon one, which the demonstrator rat has eaten, and that he's socially interacted with. And then there's cocoa rat chow, which he's never had, nor has he interacted with anybody that has eaten that food. The results of what that observer rat does is shown in the top right. There is an incredible preference for the cinnamon-flavored food, and this makes a lot of sense. If you smell a unique food on the breath of one of your rat pals, and he's not dead, well, that's probably a pretty good food to eat. And compared to an unknown food, which has goodness knows what in it, I'll take the rat chow that smells like the breath of someone's alive any day of the week, and that is exactly what rats do. Now let's track the development of such a memory over time. In this instance, we're going to use cumin as the unique taste odor demonstration. We're going to cover the rat chow with cumin, and we're going to study the development of this memory over the course of weeks, so for about a month. The rat is allowed to sleep on its normal sleep-wake pattern, and we're going to look and see which areas of the brain are involved over the course of time. And what we find is that early on in this, so in the first couple of weeks, there is an interaction between the hippocampus and the frontal cortex of the brain. So there's a synchronization, if you will, between the hippocampus and the frontal cortex of the brain that establishes this early memory. Both are required. If the hippocampus wasn't there, there wouldn't be a retention of the memory. If the frontal cortex was removed, there wouldn't be a retention of the memory. You need both, and it's the interaction that's important. But then later on, in the last half, in the final 2 weeks, the memory is in the frontal cortex only. It has changed, moved, if you will, or transformed. That memory now isn't in the hippocampus. It is in the frontal cortex only. and the hippocampus could be inactivated, much like mine was on that fateful day in June of 2014, and the memory would still remain. So here is a good example of how the passage of time with sleep causes that memory to be consolidated, if you will, outside of the hippocampus into the cortical areas of the brain. And that is extremely important, and that is the reason why I remembered my lovely wife Becky and my beautiful dogs even when my hippocampus was restarting. I want to look at one more detail of the memory as it synchronizes, if you will, between the hippocampus and the frontal cortex, because it's very, very important to see how memories not only can move about, but how they might be transformed. Now, in this environment, it involves human subjects with a fairly complicated arithmetical task. We don't need to be concerned with the details of that arithmetical task. What we really need to understand is the fact that there was a trick. There was a hidden pattern in this numerical task such that the final answer that the subject were being asked to report was predicted by the second element in a sequence. None of the subjects were told this. They were given a fairly complex numerical task to do. They had to proceed through this. They were then allowed to sleep. And before they were allowed to sleep, the main point here is nobody was told that there was a shortcut, a trick to solve this question. After the subjects were allowed to sleep, they were tested again. And lo and behold, 60% of the subjects reported that they gained insight on a shortcut or trick in solving this puzzle. This is outstanding. This says that memories, as they consolidate into the frontal cortex, are subjected to abstraction, insights, hidden rules in terms of patterns are brought out between this interaction between the hippocampus and the frontal cortex, and the frontal cortex is the one that is responsible for drawing out these rules, for drawing out these abstractions as a function of sleep. So if your grandkids are cramming for tests, it's probably a good idea to tell them you might want to get some sleep because you will be amazed at the kinds of insights and observations your brain can come to when you just let it sleep. Now let's try to tie all of this back together again. As it turns out, the hippocampus deals not only with the frontal cortex, but with several other areas of the cortex as well. So as it's synchronizing, it is talking, if you will, to several different areas of your cortex, the cortex being the outside part of your brain. And if we look at early in the stages of memory formation, this has the characteristics of a Proust story. It is rich. It is detailed. It is autobiographical. You are remembering the sequence of things that happened to you, their sensory content, what was meaningful to you, etc. But they're autobiographical, they're rich, and they're detailed. As sleep occurs, as the memory is consolidated, as it moves to other parts of your brain, it is transformed as if to a totem pole. Elements are abstracted. Rules are evaluated. Insight might be gained. The autobiographical, the you part of the memory, may well decrease. You may come to the realization that cylindrical, squirming things that are on the floor are snakes, and they are best not to be dealt with no matter what color they are. There's an abstraction that has evolutionary benefit, if you will. And so, through the course of this, we see how early on in the formation of a memory, this is a story as if Proust might have written, while as late in the formation of a memory, it's something the Pacific Northwest Indians might have carved. So it's time for Homer to weigh in again, and we'll ask Homer what his particular opinions are on this segment of the seminar. And Homer is ecstatic. He says, hey, sleep is important. It forms long-term memories. Yay, sleep. Homer, as you well know, loves to sleep, and I think he's probably going to go away and think that this is the greatest thing in the world for him to form long-term memories. But Homer has an additional point, and that point is hippocampal plus brain interaction creates totem poles. It abstracts information. Depending upon the capabilities of the brain, it may come to insightful observation. And that is one thing that sets the species of Mother Nature apart. We'll look at that in more detail next seminar. But right now, I think Homer's pretty well nailed it. These are the amazing properties of sleep and the formation of memory. Given our understandings of how memories are created, maintained, and moved around in the brain, let's now take a look at memory manipulation. Would it be possible to alter or modify memories, and would that be a good or ethical thing? I think what we can say, based on this picture we see now, is that there's one type of manipulation that's probably not ethical. In the film Men in Black, the protagonist had a device that, when activated, would completely erase the memory of an interaction. That's probably not a good thing. That's probably not an ethical thing, even if we could do it. Mother Nature gives us memory to remember, unpleasant situations for a good reason, so that we don't repeat them. However, if we had the ability to alter the emotional content of a memory, would that be a good thing? And that, I think, is quite true. As an example, let's take anxiety disorders. Now, these disorders are very common. They affect millions of lives in the United States and around the world. They reflect intense emotional dysfunction from soldiers returning from a tour of duty, irrational fears of animals or of heights, associated with abusive relationships or instances of rape. And 30% of our spending in the United States goes to some form of anxiety disorders. The cost for the economy is significant. Over $45 billion of direct costs are spent trying to alleviate the suffering that comes from anxiety disorders. If we could separate the emotional dysfunction from those memories, would that not be a good thing? Would that not be a good thing to use this technology and understanding we've investigated today? Let's take a look at it as an example. The example I want to use is PTSD, post-traumatic stress disorder. It occurs very often from soldiers returning from a tour of duty, and it's thought, under current research, to dramatically involve overgeneralization. And by that I mean that there's a memory of combat experience that has an element, some kind of burning wreckage, let's say, and that when, after returning home, when the soldier experienced something that's similar to that, like a backyard fire pit, that there's an overgeneralization. We've heard how the hippocampus can jump to conclusions or perform something called pattern completion. And this is an instance of where, in a PTSD sufferer, those two contexts cannot be distinguished, so they're combined together and the soldier is thrust back into the intense emotion of combat experience. Someone with a healthy context discrimination can separate those two environments. The backyard fire pit is a separate context than the combat experience. Therefore, once the soldier returns, there's not the overgeneralization, there's not the intense emotional dysfunction associated with contact with everyday experiences like a backyard fire pit. Since we're dealing with context, our immediate suspicion is perhaps the hippocampus is involved. And yes, indeed, it clearly is. But what about relief? How can we go about relieving the symptoms of this debilitating anxiety disorder? Well, it turns out the best way to do this is to grow new cells in the hippocampus. Now, in a normal hippocampus, in your hippocampus and my hippocampus, we do grow new cells throughout the course of our life. The hippocampus is one of a very few parts of the brain where new cell growth occurs throughout the duration of life. It's called neurogenesis. However, stress has an adverse effect on the growth of new cells. Combat experience is the textbook definition of stress. So from the exposure of combat, we probably have a decline in the growth of new cells growing in our hippocampus. And the bottom right-hand portion of this slide describes a typical growth scenario within the scope of the hippocampus. Now, it turns out the passage of time, certain kinds of anti-anxiety drugs, electroconvulsive shock, exercise, and meditation can all have positive effects on the growth of new cells within the hippocampus. The time course is noted on the bottom right of this slide. It will take 2 to 3 to 4 to 6 weeks for this kind of treatment to result in acceleration of new cell growth in the hippocampus. That matches the duration of psychotropic drugs in terms of when they can have an effect on behavior of PTSD sufferers. This is a new insight. It originates from research quite recently, and it gives us the ability to now put an understanding of how PTSD involves a lack of discrimination of context, and it gives us hope that with various avenues of treatment, we can alleviate the emotional dysfunction that comes from this anxiety disorder. Now, an exciting aspect of our understanding of memory and the hippocampus involvement, etc., gives us new therapeutic avenues for treating anxiety disorders. And we utilize the fact that the hippocampus is always learning. Because of that, what we can do is combine non-fear memories to reduce future anxiety from fear memories of the past. So, for example, a soldier suffering from PTSD based on previous combat experience can, in a safe, supportive environment, recollect those fear memories. And remember, the cells in the hippocampus that encode for a memory are the ones that recollect that memory. But those memories are going to be brought forth in an environment of measured breathing, of general wellness of the body, etc. And so therefore those fear memories are going to be intermixed with non-fear memories, and that is what is going to be subject to the hippocampal cortex interactions that we talked about in this seminar. That means using non-invasive techniques, not with drugs, not with electroconvulsive shock, we can reduce future anxiety from fear memories by coupling them with non-fear memories and their recollection. This is a wonderful avenue of therapeutic approach. It deals with meditation, it deals with exercise, and it's an exciting area of research that we'll hear more and more about in the future. But it also has an implication, and that is memory is really the last retrieval of an event, not the original event. If I'm asked to recollect an event that happened a long time ago in the past, I'm not going to get the original memory of the event. I'm going to get that memory as it's been recollected over time and coupled with all the other context that I had when I was recollecting that memory. Now that has implications for eyewitness testimony, especially as it relates to, events far away in time. Our legal system is grappling with that. Neuroscience can inform those discussions, but really new legal scenarios need to be envisioned for what we now know to be the dimensions of memory. So it's time for Homer to weigh in one last time in this seminar. Let's see what he thinks about the subject of memory manipulation. Homer says, "Your mom was right. You should face your fears." My mother told me that. I don't know if your mother did. But I think in the light of this research on the brain, the hippocampus, the storage and modification of memories, what we can see is that by bringing up your fears in a safe, non-fear environment, one can alter the composition of the context of that memory. That is potent. and that can be assisted with meditation, exercise, etc. And I think that's important as we learn how to deal with anxiety disorders and other things that affect a large portion of our society. And then the second point Homer would say is, and why don't you try exercise and meditation before things like drugs and electroconvulsive shock? I don't know anybody that would ever want to try electroconvulsive shock unless they had to. What is amazing now is the amount of scientific data that is coming out in support of exercise and meditation for its beneficial effects on the hippocampus, on the brain in general, on the body in general. And that is significant, again, as we work to manipulate the memories that underpin a significant source of suffering in our society. That concludes Seminar 3, The Structure of Memory. In Seminar 4, we'll look at the question, what is really so unique about human brains? We've talked a lot about the basic processes that underpin the brains of most of the mammal world. In Seminar 4, we'll look at what is the uniqueness of the human brain when compared to other species. We'll see some fairly surprising results. One is shown on the bottom left. How is the search for bananas in the forest environment of Africa, and what has that got to do with the processing and shape of our brain? You might be surprised to find out. The right-hand part of this diagram is a sculpture of the itinerant Japanese prince Kuya. Kuya lived in the 10th century and was a legendary practitioner of Nembutsu. Nembutsu is practicing a mantra called the phrase of the Buddha. In Japan, there were 6 syllables in this phrase of the Buddha, and the little figures that are coming out of his mouth are meant to represent that particular mantra. Kuya is repeating that over and over and over again. So one thing we'll talk about in Seminar 4 is language. The other thing we'll talk about is what kind of brain created such a sculpture. This sculpture was crafted in the 13th century. Look at the workmanship. Consider the brain that came up with the thought of making this sculpture. Consider the brain that came up with thinking about the language that would come out of his mouth. Consider the brain that thought at all about repeating the phrase of the Buddha as a way of achieving nirvana. How are all of these things wrapped into the human brain? We will not get answers to all of these questions, but we will take an amazing journey into the scope of the human brain.